Okay, so now that we've learned a lot of the basic principles of engineering economics, it is important to start adding, let's call it a dose of reality. What does that mean? Well, reality check. A lot of what we've been doing has involved estimates, and we've talked about estimates, of course, and we've also talked about the fact that estimates are subject to some, they're estimates, right? They're not hard numbers, and we use them as hard numbers for our analysis, and a lot of the times that's not realistic. So usually a single value is selected to represent the best estimate that can be made, and the economic analysis was conducted assuming these estimates were correct. But how do we explore the idea that they may not be? That instead of having estimates in reality are more than just a number, they are a range. So instead of saying, okay, the estimate is 5,000, to be perfectly honest, it could be as low as 4,500 and as high as 5,500. I mean, it could be something like that. So how do we incorporate that into our analysis to make sure that we are taking into account the fact that numbers cannot be, relied on that heavily, not all numbers at least. Okay, so decision making is fraught with risk and uncertainty. Decisions under risk are those where the decision maker can estimate probabilities of occurrence of particular outcomes. Now, decisions under uncertainty are those where the estimates of probabilities of the several unknown future states cannot be estimated. So in this chapter, we are going to talk mostly about uncertainty and a little bit about risk. Risk is something a little more complicated and a little over the scope of this class, in the sense of what we have to understand, that there are risks in our decisions. There's also a lot of math that goes into risk that isn't necessarily a prerequisite for this class. So we are going to kind of see the basic principles so that we understand the role of risk and uncertainty, and we won't necessarily calculate every single thing that could ever happen. So I also know that a lot of you may or may not have taken statistics at some point, or probability and statistics at some point before. Many of you have not, which is why I'm going to give you some basic definitions, but I am very aware that a lot of this might be sort of something we glaze over, and we're just going to use it for our purposes. So possible inaccuracies of cash flow estimates are, so four major sources of uncertainty are present in engineering economy studies. What's wrong with me? Sorry. So possible inaccuracies in cash flow estimates. So again, some of the information we might have might not be accurate. The type of business involved in relation to the future health of the economy. So as the economy fluctuates, gets better, gets worse, so will our cash flows, and a lot of that stuff we can't really control. So we need to incorporate that. Also, the type of physical plant or equipment involved. So some equipment or some kinds of machinery are more prone to giving you unreliable or uncertain results. And also the length of the study period used in the analysis. So the longer the study period, the more subject it is to uncertainty or unreliability. Because if you think about it, if I'm going to talk about the cash flow of my company, let's say I sell, I don't know, phones, right? I might be able to very accurately estimate my demand over the next, let's say, 2 or 3 years. But what if I'm doing a study period of 50 years? Is it realistic that I can estimate with certainty how many phones I'm going to be selling in 50 years? Probably not. Think of how much things have changed over the last 50 years. Actually, 50 years ago, cell phones did not exist. So we are going to have to take all of these things into consideration when we try to estimate uncertainty and risk. Now, let's go through a little bit of probability. Probability is the likelihood of an event happening in a single trial. It also describes the long-run relative frequency of an outcome's occurrence in many trials. So let's think about a coin toss, right? So what is the probability of in a single event of getting heads, right? That is a different question than if I say, what is the long-run relative frequency of an outcome's occurrence? So it's different to say, well, how many heads will I get if I flip a coin 100 times? Now, you might be thinking, well, it's 50% for one and it's 50 times for the other. Isn't that the same? But that's, and yes, that's true, but it's important to distinguish between those questions. Probabilities must follow the following rules. First of all, a probability is any number between 0 and 1. So we hear probability as percentages. You can't have anything that have more than 100% probability or less than 0. So something will have a probability of happening of 70% or 35% of 65%, whatever it is. And if we have several outcomes, each outcome will have its own probability, and the sum of those probabilities has to be equal to 1. So for instance, for a coin, we have a 50% probability or 0.5 of it falling on heads and 0.5 of falling on tails. 0.5 plus 0.5 has to be equal to 1. We can't say that it is 40%, the probability is 40% of heads and 50% of tails, because what about the other 10%? Then we would have a 10%, maybe 10% it'll fall on its side, but it has to add up to 1%. If it's less than 1, we are not considering one of the options. And there's all these distributions, and this is where I'm going to tell you kind of like, these are things that you don't need to, that are part of what we're doing, but you don't need to know them yet. If you do, that's awesome. That means you're probably taking some probability statistics in the past. So there are two kinds of distributions. There's continuous distributions and discrete distributions. Within continuous distributions, we have the normal distribution, continuous, uniform, exponential, and y-ball. And in discrete, we have binomial, uniform, geometric, hypergeometric, Poisson, and custom. There's lots of different ones, and these kind of shape what we're going to do here. But I'm just going to give you the formulas. So, okay, let's talk about estimates a little bit. So we saw in sensitivity analysis that sometimes a small change in one of the costs or benefits can make us change our decision. And if we haven't covered sensitivity analysis, if you haven't seen those, then we will get there. Sometimes I put this chapter in different order depending on what I'm trying to do. So let's talk about, but it's really a thing. So let's say that I'm giving you this equation and I'm telling you that my first cost is $10,000 and my benefits for the next 5 years is going to be $2,000 per year, and that's all the information I give you. And let's say that after and with an interest rate of 10% and all of that information, I can calculate that, ooh, it's a great option, keep it, right? Well, yeah, but now what if instead of it costing me $10,000, it cost me $15,000? The question is now, am I going to change my decision? Now, the difference between 10,000 and 15,000 is large, but what if there are situations where the difference between a first cost of 10,000 and a first cost of 10,500 will lead to a different decision, a bad investment versus a good investment, and that's where we need to be very, very careful. So it is actually more realistic to describe parameters with a range of possible values. There's the optimistic estimate, the most likely estimate, and the pessimistic estimate. So I think that I'm going to be making $2,000 a year, but it could be as high as 3,000 and as low as 1,000. Okay, so now I have some calculations to make. All right, so here is based on a distribution called the beta distribution, we can estimate our mean value to be calculated with the information of optimistic, most likely, and pessimistic to work like this. So the mean value of something can be O, that's not a 0, it's an O, plus 4 times n plus p divided by 6. So it's 1 plus 4 plus 1 equals 6 divided by 6. So it's an average, but it's a weighted average where the most likely weighs 4 versus 1 and 1 in the optimistic and pessimistic values. So there's clearly more, it's more likely that it is the most likely estimate. Otherwise, it wouldn't be called that. And this helps us. So if you find that these are evenly distributed, so if this is 2,000, this is 3,000, and this is 1,000, it'll come back to 2,000. But what if my most likely estimate is 2,000 and my optimistic is 3,000? But what if my pessimistic is 0? Now that is a big difference right there, and it turns out that your mean value will be lower than your most likely estimate.